Hey everyone, and welcome. Today, we're diving into one of the coolest and most fundamental connections in all of physics, the magnetic effective current. It's this invisible force that literally shapes our entire world, linking the electricity buzzing in your walls to the simple magnet on your fridge. Let's dig in and see how it all connects. So let's kick things off with a simple question. What in the world does the electricity flowing through a wire have to do with a refrigerator magnet? I mean, they seem like totally different things, right? One is all about powering our lives, and the other just kind of sticks to stuff. Well, it turns out they're actually two sides of the same incredible coin. And figuring that out, it changed everything. So our story really begins with a pretty shocking discovery. I want you to imagine you're a scientist, you're in a lecture hall, and all of a sudden you see a compass needle twitch, but not because there's a magnet nearby, but because of an electrical wire. Whoa! That single, tiny movement was the first clue that there was a whole new force at play in the universe. Okay, before we get to that moment of discovery, we gotta meet our main character, the magnetic field. It's basically this invisible area of influence around a magnet or a wire with current flowing through it. And here's the key. It's a vector field. Now that sounds complicated, but all it really means is that at every single point in that space, the force has a strength and a direction. It's like an invisible web of tiny arrows, all pointing where the force is going. And that brings us to Hans Christian Ørsted, back in 1820. The story goes that during a lecture, he passed an electric current through a wire, and he just happened to notice something amazing. A compass needle sitting nearby totally deflected. This super simple observation was nothing short of revolutionary. It was the first concrete proof that moving electricity creates its own magnetic field, revealing this deep, hidden link between two forces everyone thought were completely separate.
So Ørsted basically kicked the door wide open. But now what? I mean, once you know a connection like this exists, you've got to define the rules. How strong is this new magnetic field? Which way does it point? The race was on for scientists to write the laws that governed this whole new phenomenon.
And that's where the Biot-Savart law comes in. Now, don't worry about trying to decipher all the math on the screen here. The best way to think of this is like the master recipe. It's the fundamental formula that lets you calculate the exact magnetic field from any tiny little piece of a wire carrying a current. It's really the foundational tool for predicting this new force. Okay, I know that formula looked a little intense, but what it's telling us is actually pretty intuitive when you break it down. The magnetic field gets stronger if you have more current. Makes sense. It also gets weaker the farther away you are, just like gravity or a light bulb. But here's the really unique part. It all depends on the angle. The force is strongest when you're at a 90-degree angle to the wire, and it goes to 0 if you're right in line with it. Weird, right? Now, if you're familiar with electrostatics, it's super helpful to compare this to Coulomb's law. You can see they have a lot in common, like how they both get weaker with distance. But here's the real kicker. The source is different. An electric field comes from a charge, which is just a point. It has no direction. But a magnetic field comes from a moving current, which is a vector. It's got a direction. And that's why the angle is so incredibly important for magnetism. Now, while the Biot-Savart law is the master formula, it can be, let's be honest, a real pain to use sometimes. So for situations with a lot of nice, clean symmetry, think of a long, straight wire, physicists came up with a powerful shortcut, Ampere's law. You can think of it as a much more elegant way to get the same answer when the geometry is playing nice. All right, so we figured out how a current can create a magnetic field, but what happens when you put something into that field? I mean, what does this invisible force actually do to things? Okay, and this is where things get really, really interesting. A magnetic field only pushes on a moving electric charge. If a charge is just sitting still, it feels absolutely nothing. But the second it starts to move, bam, it gets pushed by something we call the magnetic Lorentz force. And get this. The push is always perfectly sideways, perpendicular to both the direction the charge is moving and the direction of the magnetic field itself. This constant sideways push leads to some absolutely beautiful motion. If a charged particle flies into a magnetic field at a perfect right angle, that sideways force traps it in a perfect circle. It just goes round and round. But if it enters at any other angle, it creates this gorgeous spiral path, a helix. It's moving forward while it's also looping around. That angle of entry literally dictates the entire dance. So let's scale this idea up. A wire with current is really just billions and billions of charges all moving together, right? So what happens if you put two of these wires next to each other? Well, they interact. The magnetic field from wire number 1 pushes on all the moving charges in wire number 2. And it all boils down to a super simple rule. If the currents are parallel, going in the same direction, they attract. And if they're going in opposite directions, they repel. Okay, these rules are fascinating, for sure. But what are they actually good for? Well, it turns out this invisible force is the absolute key to turning electricity into motion. Let's see how we actually put this thing to work. The secret to pretty much every electric motor is creating rotation, what we call torque. And the principle is so simple, it's beautiful. You take a loop of wire, you put it in a magnetic field, and then you run a current through it. The magnetic force on one side of the loop pushes up, and the force on the other side pushes down. This pair of opposite forces creates a twist, a torque, that makes the whole loop spin. And just like that, you've turned electricity into motion. And this exact principle is the heart and soul of a classic piece of lab equipment, the moving coil galvanometer. You can see all the parts here, the coil, the magnets, the little needle. This whole device is a direct physical application of that magnetic torque we just talked about, and it was designed for one specific job, to measure electric current. So here's the genius of it. You pass a current through that coil, which creates a torque that tries to make it spin. But there's a little spring in there that pushes back. The needle ends up settling right where those two forces are perfectly balanced. So if you have more current, you get a stronger magnetic force, which pushes the needle further against the spring. It's an absolutely brilliant way to make an invisible current totally visible. We've gone all the way from a twitching compass needle to the inner workings of electric motors. But you know what? The story has one more truly profound twist. A cosmic connection that reveals just how deep this relationship between electricity and magnetism really goes. See, in physics, there are these fundamental numbers, these constants of nature, that basically set the rules for how strong forces are. For electricity, there's a constant called epsilon naught. For magnetism, there's one called mu naught. And for the longest time, everyone just thought they were two totally separate, unrelated numbers that we measured in experiments. But they aren't random at all. And this is the ultimate connection. It's absolutely mind-blowing. When you take mu naught, the number that defines the strength of magnetism, and you take epsilon naught, the number that defines the strength of electricity, and you combine them in this very specific way, you get exactly c, the speed of light. Let that sink in. The constants for electricity and magnetism are literally woven together to define the speed limit of our universe. This equation proved that light itself is an electromagnetic wave, and it unified electricity, magnetism, and optics into a single gorgeous theory. So that's where we land. A simple observation of a compass needle took us on a journey to understanding motors, and then, ultimately, to understanding the very nature of light itself. It really makes you wonder, if electricity and magnetism are just two faces of the same fundamental force, what else in our universe is secretly and deeply connected, just waiting for us to find the link?